All right, well, it's 11 a.m., so we will get started and recognize that there'll be some people joining on in. Good morning, everybody. I'm Paul Gross, meteorologist at WDIV in Detroit, and my co-moderator, McCall Vrydaghs, chief meteorologist at WHIO-TV in Dayton, Ohio. We're not too far away geographically, and we're here as members of the AMS Committee on the Station Scientist, and the committee was formed many years ago, actually, with the sole goal of encouraging and enabling broadcast meteorologists to add more science and environmental information to their weathercasts. And this webinar is part of the enabling part. We are some of the most busy people in the entire world, and we work under a lot of deadline pressure. It is hard to sometimes stay current in our science. And so this is the first in what's going to be kind of a periodic series of webinars that we're going to put together. They're going to be quick hitting webinars. Our speakers are generally going to speak for 15 to 30 minutes. We'll open it up for some questions and then bam, we're done. And it'll be real quick, easy education and things that you'll be able to, I guess we'll call it news you can use. So things that you'll be able to take to air and actually be able to report on. So with that short intro, let's now send over to McCall and you can introduce our special guest today.
Well, thank you so much, Paul. And as we get into this, you'll notice perhaps on the right-hand side of your screen, there's a questions tab that if you have any questions about Jim's presentation, just make sure to drop those in there. We will be going through those at the end of the presentation and hopefully have a really good, thorough discussion. We'll get right to it. And I wrote it all down, Jim, because there's a lot here for your bio, and I want to make sure that I get it all right. So Jim Kozin is an atmospheric research scientist in the National Oceanic and Atmospheric Administration, also known as NOAA, Climate Science and Service Division. His research focuses on hurricanes and their relationship with climate and climate change. Jim has been awarded the Department of Commerce Gold Medal and the NOAA's Administrator's Award for his contributions to the international and national climate assessment process, and the NOAA Bronze Medal Award for his work with the U.S. National Hurricane Center. He earned his PhD in atmospheric science at Colorado State University. Jim, we are so excited to have you here and cannot wait to hear all about how tropical cyclones and climate change may be impacted by, or how climate may be impacting tropical cyclone development. So I'll let you take it away.
Well, thank you so much, McCall, and thank you, Paul. I really appreciate the invitation to this. This is a terrific opportunity to get information out there about a topic that all of you, I'm sure, are asked about very, very often, especially nowadays. Again, my title is Tropical Cyclones and Climate Change. What do we know? I think Paul had what do we know, what don't we know, but I'm obviously taking the more optimistic side here. Also, what we don't know is something that we know about. So, and the rest of my talk will be much clearer than that, hopefully. So I wanted to start with just some basic physical understanding, right? That's really the best place for us to start. Do we have some sense of what we expect in terms of how tropical cyclones, and by the way, tropical cyclone is just a generic expression for these storms. They're called hurricanes, of course, in the Atlantic and also in the eastern North Pacific. They're called typhoons in the western North Pacific. They're called cyclones in the Bay of Bengal in the southern hemisphere, but they're all the same animal. And we just generically call them tropical cyclones, which we typically bring down to TCs. So when I say TCs here, I just mean tropical cyclones or hurricanes. So again, we want to get a sense of what we understand because that's our foundation. What do we expect? How do we expect tropical cyclones or hurricanes to respond to climate change? And the first thing that we should talk about is the wind intensity. And this is usually how we think about these storms. How strong are they in terms of how strong are the winds? And that's what the Saffir-Simpson categories are based on, is wind speed. So a category 5 is obviously much, much stronger wind intensity than a category 1. So there are two primary factors that tell us how strong a hurricane can get if everything else is optimal. And that's called its potential intensity. It's the potential, what it can reach, everything else optimal. This is based on some pioneering work from the 80s by Kerry Emanuel. And the two primary factors are ocean surface temperature and also heat content, which is, more than just the surface temperature, but how deep that heat goes. And also the temperature and the moisture state of the atmosphere. And that's a vertical, you could think of that as a vertical profile, how the temperature and moisture from the surface up to, say, the tropopause, what their profiles look like. So potential intensity depends on what we would call the moist thermodynamic state, which is just a fancy way of saying temperature and humidity. And that theory is based on a Carnot cycle heat engine. We don't certainly need to go into the details of that now. Now, again, that'll tell you how strong a hurricane can get. So the way to think about that is, okay, we have an environment. If I were to pick up a hurricane from a jar somewhere and drop it down right in that place, how strong could it become? Now, the kind of factors that will keep it from reaching its potential intensity would be something like vertical wind shear. The way that the winds in the environment change with height will greatly affect the efficiency of that heat engine and keep it from reaching its potential. Okay, so what all this has to do with how tropical cyclones respond to climate change is, if climate change does increase potential intensity, and it does, and all other factors don't change to counteract it, then we should see a shift towards stronger storms. And we should have seen it by now. So the question then is, do we? And the answer is yes. So this is based on some fairly recent work. The historical records of tropical cyclones, which usually comprises their position and intensity, wind intensity, every 6 hours during their lifetime, have a lot of problems as you go further back in time. But we can, within the satellite era, we can homogenize those data and remove the inconsistencies. And then we can do a global and a regional analysis on trends using that with confidence that the trends are real and not just due to technological advances. So when we do that and we look globally, we find that if we just count the number of times, those 6 hour periods, the number, which are called fixes, by the way, the number of these 6 hour periods where hurricanes or tropical cyclones globally are category 3 or stronger divided by just the number of times that they're just a hurricane, there's a very significant and substantial trend towards more. So the proportion, the likelihood of a hurricane being at major hurricane status is increasing with time. It's about 25% more likely now globally than it was about 40 years ago. In the North Atlantic, it's very steep. It's more than doubled. And just to make sure that the Atlantic is not driving the global trend, we can remove the Atlantic data and then look at the global trend, and we see it's still clearly an increasing trend. So we are seeing a tendency towards more major hurricane intensities. And it's a steady trend, and it does not appear to be explainable just through natural variability. Really important point here and throughout this talk is that the storms that really, really make a difference as far as humans go, or just in terms of communities along the coast in particular, is that almost all of the mortality comes from major hurricanes. There are certainly cases where you can get a weaker storm dropping a lot of fresh water and maybe cause a mudslide and some significant flooding. You could have loss of life. But by and large, the lion's share of the death and destruction associated with these storms is caused by major hurricanes. So those are the ones that we care about. And what we see here is that they're more likely now than they were 40 years ago. And the next question would be, are they projected to get stronger with continued warming? Because the planet is going to continue to warm for a while now. I mean, hopefully we'll get it in check before 2100, but we're projected to just keep getting warmer at the moment. And so this is all based on numerical modeling studies. The last thing we looked at was based on data. This is based on model projections, climate model projections. And the answer is yes, we have high confidence that average hurricane intensity or tropical cyclone intensity will increase as the planet continues to warm. The mean projected increase in the peak intensity that these storms reach is about 5% under about 2 degrees C of warming. Now, This is also a recurring theme in this business of extreme storms or extremes in general, is that we get a little bit too caught up in talking about how much the average changes. And those do not really tell us what's important. And I'm using a figure here from the IPCC that they use temperature, surface temperature here, but it's true of any meteorological measure. You have a distribution of these intensities from weak to strong, and you have a shift of the distribution towards stronger. That usually translates to a small change in the average, but very, very large changes out in the extreme ends of things. And so for surface temperature, what that means is, it's about 5% increase, or whatever. It's a few percent increase, or it's a degree increase on average, but the number of heat waves that you get from that goes up enormously. Those are the things that matter to us. It's the extremes that really affect us. So this is an important point that's sort of ubiquitous. It's always there when we talk about how things are changing due to climate change. And it's important for us to get out of the mindset of what's the average change. And I'm sure all of you have had people say, well, what's the big deal? The temperature's only gone up a half a degree C, which is about a degree Fahrenheit. What do I care at 1 degree Fahrenheit? And that's a reasonable thing to say, because in your world, in your local world, 1 degree Fahrenheit, the difference between 78 and 79 is not much at all. But these small changes in the averages have these huge impacts on how the extremes are behaving. That's really key. Okay, so that is exactly what we find with tropical cyclones. These small changes in average wind speed translate to very large changes in the proportion of your really, really intense TCs. The category 4 or 5 hurricanes can go up by about 13%. And these, again, are the storms that we really, really need to worry about. Okay, that takes care of wind intensity. We have pretty high confidence that it has changed. We have pretty high confidence that it will continue to change. The next thing we have pretty good confidence about is how much rain falls out of them. These are rain rates. So if you're following the storm around, how much water is coming out of them? Say, in millimeters per second, or inches per hour, something like that. Well, we know it is very simple physics. The amount of water vapor in the air increases on average by about 7% per degree C of warming. And I think we all know that hurricanes are really, really good at turning water vapor into rain. So right out of the gate, we know that, yes, for sure. I mean, it's almost a physical imperative that if you warm the air, you're going to have more water vapor. If you have more water vapor, you're going to get more rain, and hurricanes are certainly going to rain more. It's kind of hard to measure this from past data because the rain gauges are scattered. There's a lot of data issues, particularly globally, and unfortunately, rain gauges are a lot less accurate in high wind environments. So you can imagine they wouldn't be all that reliable in hurricane environments. But we do have high confidence that it has increased, and we have high confidence that it will continue to increase based on model results. And just for kicks here, what else do you think could lead to more rainfall besides just increasing their rain rates? Well, the answer to that comes with a hint. Think of Hurricane Harvey. The reason all that rain fell on the ground is not so much that Harvey was raining harder, that much harder than other storms. It's because it stopped moving. It just sat there and rained in one place. So there are two factors in terms of local rainfall. This is in terms of how much rain falls out of the hurricane, regardless of how quickly it's moving along. Okay, so that segues into this. We talked about now intensity, and we talked about rain rates and rain in general. I'm going to talk about TC frequency later. Another very important question is whether hurricane tracks have been and will be affected by climate change. There's two ways this can happen. One is kind of what we would call along the track. So changes in their speed of forward motion, how quickly they move from one point to another along their tracks. And the other one would be actually track shifts. Now, as we just touched on with the discussion of Harvey, changes in forward speed can have really profound effects on local rainfall amounts. It could also affect wind damage because the amount of damage to a structure is not just based on how strong the wind is, but how long the duration of the event is. So slow-moving hurricanes are just bad. There's nothing good about them. You want them to get out of your neighborhood as fast as you can. And track shifts can have a very profound effect on exposure patterns. So places that may not have been exposed to hurricanes that much in the past may find themselves exposed to them quite a bit more in the future. So track changes really, really do matter here. It's not just how strong the storms are, how many there are, it's where they go and how they get there. Well, we can go back all the way to 1900 if we constrain our data to just be over the continental United States. This is our most reliable data set for our longest period of time. And when we do that and we measure how quickly these storms are moving from one point to another, we find these very distinct and significant decreasing trends. The storms are slowing down. So this panel on the left here just shows all the different points that went into the analysis. These are storms that are either just about to enter or move over the coast, and so they're still out on the water, but 6 hours later they're on land, or they're on land. And when we look at their average speeds, or their average or their median, or pick the average of, say, how quickly or how quickly are the storms slowing down, bad way to say it, for the slowest storms versus the fastest storms. Then we see this plot just in the middle here. This is the actual translation speed. Translation speed is the same as forward speed. I always think of it as a top, spin a top, and that's your hurricane, and put it on a piece of plexiglass, and it'll just sit there and spin. Now pick up one end of the plexiglass, it'll start to slide down. The rate at which it's spinning is what we think of as wind intensity. That's your category 1 through 5. The rate at which it slides down is pretty much completely independent of that. They're independent of one another. So it can move fast and spin fast, it can move slowly and spin fast, etc. So here, these storms are slowing down in their translation speed, regardless of how fast they're spinning. And the median slowdown is about 14% over this 120-year period. The slowest 10th percentile of these storms has slowed down by 24%. That's a really, really big change. Now, again, we said that the rain rate increases by about 7% per degree C. There's been about, give or take, 1 degree C warming since 1900. Local rainfall goes like rain rate divided by speed of motion. And so if you just plug in those numbers here, your local rainfall changes by 41%. That's a huge number. This is a very large number to have something that we can observe to some extent. So we would expect the change in local rainfall that over the continental U.S. has experienced from hurricanes has increased by about 41% over the past 120 years. We also, when they slow down enough, we call them stalled. It's kind of a colloquial term. It's not super well defined, but it's kind of like one of those things where you know it when you see it. We've recently had a number of stalled systems. This past season, we had Sally over the U.S. We had Ada over Nicaragua. Hurricane Dorian, of course, stalled over the Bahamas. Devastating situation. Florence stalled over the Carolinas. Harvey, of course, stalled over Texas. It happens globally. Cyclone Idai stalled over Mozambique. And this seems to be happening more and more often, which is consistent with the fact that they're slowing down. So this panel here on the left, this plot just shows that the number of hurricanes that stall for 2 days or more, that has a significant trend as well. And there is increasing rainfall associated with that. Okay, so we've got that. The slowdown also appears to be occurring globally. We're not 100% sure why it's happening yet. This is all relatively new research, but it's the amount of slowdown you can see by overland in different regions. You see the numbers there. That minus 16 is slightly different than the minus 14 we just saw, because this is the change in the mean, and that was the change in the median. They're very similar, but not quite identical. Anyway, these are the slowdowns that we see globally. We're not sure why. It may be due to the fact that the Arctic or higher latitudes are warming more quickly than the lower latitudes are. This is called Arctic amplification. So if the high latitudes are warming more quickly than the low latitudes, or the poles are warming more quickly than the equator, the temperature difference between the two is getting smaller and smaller. That temperature difference is responsible for the pressure difference. And if the pressure difference from low latitudes to high latitudes becomes less, then the circulation slows down. And these storms are very similar to corks in a stream. They're not completely independent of their environmental flow, but they are largely independent. They're just carried along in the environmental flow. So if you slow down the environmental flow by this Arctic amplification process, then you would expect storms in the subtropics and mid-latitudes to generally slow down. And that does seem to be what we're seeing here. It's a hypothesis at this point that needs to be tested more, but it seems like a reasonable one. Track shifts would be the next thing. Check my clock here. Track shifts have also been noted. Tropical cyclones globally tend to have migrated poleward in most regions, not in the Atlantic, and there's some various reasons for that based on regional effects. But this increased, you get increased tropical cyclone exposure due to these track shifts. And the place where these track shifts is particularly pronounced is in the western North Pacific. So this is threatening Asia. And we can zoom in on that here. And this is nice too, because it goes back and reemphasizes the importance of not just looking at how the averages change. So if we just look at the western North Pacific and we look at the latitude where these typhoons, tropical cyclones, are reaching their peak intensity, this is when they're strongest, and we look at how that's changed over the years from an early period to a late period, we see a shift in what's called the distribution, from the most close to the equator to the ones that are most close to the poles. Highest latitude, lowest latitude to highest latitude. What is the distribution? And you can see that on average, they're hitting their peak at, around 20 degrees north. And the average, you can estimate the average by where those peaks of these bell-shaped curves are. So here's the average in the early period. Here's the average in the later period. It's just a few degrees of latitude. It's not very much, a couple degrees even. But if we look at how the exposure at high latitudes has changed, it's much more than doubled. It's very unlikely for these storms to reach their peak intensity all the way up to 35 degrees north, but it's about 3 or 4 times more likely now than it used to be. So yes, it's low probability, but it's increasing enormously. So this could be considered relatively good news for the Philippines, where they're getting slightly less exposure at these low latitudes. May not make a whole heck of a lot of difference to Taiwan, which sits pretty close to where that average is, but it's going to make a heck of a difference to parts of Eastern China and Japan and Korea. So these are very important, again, to focus on how the extremes are changing. Okay, I promised I would come back to frequency, how many storms? And of course, the Atlantic had more storms last year than we'd ever recorded before, and so this is a pretty hot topic. Unfortunately, it's also the one that we are least confident about. So I suppose in the what we don't know category, this would fall more closely over there. I mean, we know a lot, and we have a pretty good idea of what we don't know, but this in terms of how tropical cyclone formation, or it's called genesis, how that's affected by global warming, we have less confidence in our physical understanding of that. We know that warming raises ocean temperature and increases heat content. That's just simple. You warm the air, eventually the ocean is going to be affected by that. It's going to absorb that heat. That's why you could swim in a lake in the summer and not in spring. that gets warmer because the air is getting warmer. Now, this is a tough one, and we don't have time to go into it, but there's an enormous amount of research being done by very, very smart people on this topic. But the atmosphere responds to warming depending on what caused the warming. So well-mixed greenhouse gases, this carbon dioxide that's fairly uniform throughout the planet, causes a warming of the ocean, for sure, but it affects the atmosphere as well, and it affects it differently than some other things might. So in this case, it tends to stabilize and dry the atmosphere, and that tends to suppress formation of these storms. And so you have these two counteracting effects, and that makes it very difficult to get a real strong bead on how things are going. I think that the takeaway here, and I should mention that what's happening in the Atlantic is a very specific to the region. There's a lot of things that have been happening regionally, and I wish I had more time to talk about it. Well, maybe I have a little bit of time. Let's do it. I think it's important, since most of you probably are talking about hurricanes and their effects on the United States. There's a very interesting thing that's happened in the Atlantic. We were polluting the heck out of the air, during the first half of the century, and then things really got bad. The Cuyahoga lit on fire in New York City. You couldn't even see across the Hudson, New Jersey anymore. I was there at the time, living there. It's pretty bad. At one point in the 70s, they said, we got to do something about this. So the Clean Air Act and amendments were adopted by the United States. Also, Europe had their own Clean Air Act and amendments throughout the 70s. And the upshot of that is that the air was cleaned up significantly. It's so much cleaner now than it was in 1970, which is a great success story. But what that did is all that pollution was keeping sunlight from reaching the Atlantic. And that's essentially, it keeps it from warming, which we would call a cooling effect, right? So you put all this stuff in the air, blocking the sunlight, effectively cools the ocean. Now we're taking that away. And so now we have the double whammy of the greenhouse gas warming that's been counteracted by this pollution that's been building up in concentration. Now we're taking that pollution away, and temperatures are really going up in the Atlantic. So there's a very, very intense regional effect that's caused by reduction of what we call pollution aerosols, or just call it pollution particles, if you like, over that region. Also, the amount of dust blowing off of the Sahara in the trade winds over the Atlantic, that also is much less now than it was 40 years ago. We're still trying to understand exactly why. But the bottom line is that regionally, there's been a lot going on that's caused the Atlantic Ocean to warm up very quickly, much differently than the rest of the planet. That is very, very likely why we're seeing these really busy seasons. And we've been in this very active period since about 1995. It's probably not due to global warming so much as it's due to regional effects. And so the takeaway here is there really is no clear evidence, and there really isn't a clear expectation that the number of storms will have increased or will increase due only to greenhouse gas concentration increases. That's important. But, and this is a really important point, is that once you do get a storm to form, once a storm does form, it's much more likely now to become stronger, to reach major category status. It's much more likely to rain more, seems to be more likely to move slowly, and it seems to be more likely, particularly in some regions, to reach its peak intensity at a higher latitude. So all those things that we have really high confidence in are once you have a storm formed. The thing that we don't have great confidence in is how many storms are we going to have? How's that going to change? And the consensus is that it probably won't change much. And some models even predict a slight decrease in the number of formations. Okay, there's other aspects of tropical cyclones that have been linked to climate change. One is that they seem to be intensifying more rapidly. We've been seeing a lot of that lately, especially last year. The research that's been done suggests that the chance of rapid intensification in the early 80s was about 1 in 100. 30 years later, it's gone up to about 1 in 20, factor 5. That's a huge change. And it doesn't seem to be explainable solely by natural variability. And then the other thing that we might ask about is size, right? We know that the size of a hurricane makes a huge difference. Hurricane Katrina would not be anywhere near as devastating as it was if it hadn't become such a large storm. And as an aside, it became a large storm because it underwent something called an eye wall replacement cycle, which is where the inner eye wall, which is generally pretty compact, forms another outer eye wall around itself. And that outer eye wall actually kills off the inner eye wall and starts to contract down to replace it. But what you get in the process is a storm that becomes much larger. And that's what happened with Katrina. And that's why there was so much storm surge, because the bigger the storm is, the longer the fetch, which is the amount of time that wind is blowing on the ocean. And that has a profound effect on the storm surge. So size matters, but unfortunately, there haven't been that many studies to see, because it's very hard to measure. How do we measure storm size? Is it where the radius of 35 knot winds are? Is it the outer closed pressure isobar, et cetera? How do we measure it? How do we even define it? So we have a general lack of studies. There may be trends in TC size, but we don't really know. There's no clear evidence yet. Hopefully people will work on that problem. And so I'll summarize here, and I think, great, okay, I think I'm within my half hour pretty closely. So what do we know? Well, it's not so clear that we're going to have more of these storms forming. But as I mentioned a moment ago, and reiterate here because it's important, once it does form, we have high confidence that it's more likely to be major, be at major hurricane intensity. It's much more likely to have greater rain rates. It's more likely, to intensify rapidly. We also have pretty solid evidence, but again, this is all relatively new research, so the more time we have for it to be tested, the better. But there's good evidence that tracks have changed and will continue to change. Forward speed is particularly of concern because these slow-moving storms are so devastating, and they're more likely to stall now than they used to be. Exposure to TCs has changed quite a lot, particularly around Asia, Southeast Asia. And so I think that when all is said and done, what do we know? We know quite a bit. It's obviously a very active topic. There's a lot of questions. There's still a lot of folks that feel like what's happening in the Atlantic is natural. There's an enormous amount of evidence to suggest otherwise. And so it's still a controversial topic, certainly, but our confidence in these links between tropical cyclones and climate change has increased enormously, even since Katrina. So we're making great progress, and there's a lot of folks working the problem. And I will stop with that, and hopefully there'll be some questions. Thanks for your attention.
Well, thank you, Jim. That was absolutely fascinating. And again, if you have a question, put it in the chat and we will forward those. We'll ask Jim your questions. But since McCall and I put in the work, we get to ask the first questions. That's just the privilege of taking this on. I want to know, Jim, we talked about the impact from climate change, but what about some of the recurring patterns like PDO, El Nino, La Nina? Any climatological impacts from those? Does that kind of mess up the database a little bit?
Yeah, that's a great question. I mean, when we talk about climate change, we have to step back and take the much broader long-term view of things. The kind of variability that you're describing, a lot of which is natural, certainly El Niños are natural. That in terms of finding trends, long-term trends due to climate change, we would call that noise. Right, we want to get rid of it. And so these studies, in particular, will do either very long-term trends on annual data, or they'll do what we call a composite study, where you take 40 years early and then 40 years in a later period and look at the difference between them. And what we do when we do that is we kind of remove a lot of that variability that you're talking about. But yes, there's absolutely all of these different, what we call modes of variability, El Nino, Southern Oscillation, operates on, say 2 to 3 year time periods. These decadal oscillations act decadally over, say, even 20 to 40 year. And they're not necessarily oscillations, they're not that predictable. They don't swing like a pendulum, but they do seem to exhibit this sort of, ups and downs. Presumably, when we're looking at these trends, these long-term trends, we've sort of accounted for those.
So I know that you're doing a lot of those annual studies, as you mentioned, and you're doing globally and nationally. One question is, maybe you've looked into it, or maybe it's something on the docket of how hurricanes are behaving dependent upon the season. We do have those late season storms in November, and we're seeing perhaps maybe stronger storms or more frequent storms. Obviously, frequency is still a question mark. But have you dived into seeing, is it leaning any way?
Yeah, another great question. And yes, there's a lot of, we can do annual averages and then look at how those are changing. And then we could also dive in seasonally. And we can say, how is the November activity changing over time? And there are definitely studies that look at that. I think maybe what might be motivating the question in this particular context is what we've been seeing in the Atlantic with these very early storms and very late storms. And again, I think that has a lot to do with the regional behavior in the basin. But it's an interesting thing. It's statistically, if you pick more points, you're more likely to find things on the extreme ends. And it's kind of like how many times you're at bat, you become more likely to hit home runs. And we simply have a lot more storms in the Atlantic now, and so the season has expanded in just a purely statistical context. There's more options for it. Now, in terms of whether or not November has systematically changed in a way that's different than the rest of the season, there doesn't seem to be a lot of evidence for that right now. It's kind of the way the whole season has changed that's causing the season length to change.
That makes sense. And that is perhaps why our now 30-year average number of hurricanes has gone up. And I'm assuming, and maybe I shouldn't, that we will eventually maybe see the hurricane season starting a little bit earlier officially rather than June 1st. What are your thoughts on that?
Yes, well, we know that the National Hurricane Center has started issuing advisories now on May 15 rather than waiting for the official June 1 start of the season. The World Meteorological Organization has asked the National Hurricane Center to consider the question of whether to change the official start of the season to May 15. So we're talking about a two-week push. I think that that's probably not a bad idea. I think that this new normal that we're in is not going to change anytime soon. We don't have a lot of evidence to suggest it will. There are these random things that can happen that can potentially bring us back to a more quiescent time, more similar to what we saw in the 80s, for instance. But it's random and unpredictable. And so in terms of what to expect, I think that we're in our new normal now, and there doesn't seem to be a lot of evidence that we're going to go back to the quiescent period anytime soon. So yes, I think May 15 would be completely supportable to move the official start to May 15th now.
And if anybody has a question for Jim, type it in the chat and we will ask those to him. I have one last one for myself, and that is, as you know, the satellite era began in the, mid to late 1960s. So do we really need to just focus on kind of what has happened when we've had that opportunity with satellite data? I mean, because I know that there is some data that we have like landfall, in the period pre-satellite, but I mean, pre-satellite, you don't know if a storm necessarily went to Cat 5 status and then it made landfall as a Cat 2. There are gaps in that record. So do we really just need to focus on what's been happening over the past, 60 and 55 years or so?
Well, I think the answer is yes, but also with an explanation. I mean, you're absolutely right. The historical data we cannot rely on. There are plenty of trends that we'll find if we analyze it, but we don't trust them because of what you're saying. There must have been, storms out there in the eastern Atlantic. If they didn't hit an island and have someone record it, maybe a Jesuit who was on the island, that's a lot of our information comes from their journals when we go really far back. If it didn't run into a ship, And how on earth are we going to know whether it was a category 4 or a category 5? No question. We just simply do not have data that are good enough to go back that far and measure these things. And like you say, the over continental US and the landfalling record and that forward motion speed, we have confidence, more confidence back all the way to 1900. But so I guess, yes, in general, when we do global studies, in fact, we don't even go back to the 60s, we go back to the late 70s. 79 is the earliest day from that study where we found the changes in the intensity or the proportion of major hurricanes. So we do have to limit ourselves to the satellite era for many things. But again, like you say, for some things we don't, like the landfalling record, we can go back to 1900. If we're not looking at things that matter, that intensity matters, like forward speed, as like I said, with the top analogy, has nothing to do with the actual spinning speed, then we don't care how well we're measuring the spinning speed. Doesn't matter if it's category 4 or 5. So we remove that uncertainty at least, and now we only have the uncertainty in the position. So the answer to your question is yes, in general, we want to stick to the satellite era, but there are other measures that we can look at that allow us a little bit more latitude for how far back we go.
We have about 15 questions or so in the chat, so I'm going to try and organize them a little bit. I'm going to take 2 questions here and combine them into one because I think they kind of go together. First part is from Allison Ray, and she wants to know which warming is greater, warming from greenhouse gases or local warming from lack of pollution. That's kind of part 1. And then Sean Sabaletti asking, regarding that pollution over the North Atlantic, how does that relate or negate to the MAO or AMO? Sorry.
AMO, right? Sure, great question. In terms of the relative, the relative warming between, say, greenhouse gas warming and, let's say, pollution reduction warming in the Atlantic, I think the warming is probably being dominated by the pollution reduction. But even if it wasn't, here's that key that gets back to that complicated thing we have with these, is that the way that warming due to globally well-mixed greenhouse gases, the way that that affects the potential intensity of a storm is much different than the way that regional pollution reduction affects it. The pollution reduction is much more effective at raising the speed limit, at raising the potential intensity and allowing stronger storms to form than maybe we've ever even had before. And so even if they were equal, the effects on the hurricanes are greater due to the regional warming from the pollution reduction. And that's a really key feature, but again, comes back to this complexity that's so hard to convey. It matters what caused the warming. But there is certainly quite a lot of warming from these external factors of the pollution and the dust. And so that would dovetail into the next question about the AMO. This is a very, very important topic right now. And there's, again, so much research being done on that topic. But the AMO historically has been a bit of a red herring, because what they did is they just took sea surface temperature over time, say annual, and then they detrended it, saying this is that long-term trend we're going to assume is the warming due to greenhouse gases. And so the assumption at that time, this was a while ago, was that we've removed the human-caused, the anthropogenic part from this time series, and all that's left is natural. Well, there's huge evidence at this point now to say that is absolutely not true. What we do now is we call the observed changes Atlantic multidecadal variability. That is what it is. It's variability. We observe it, and it seems to be happening on these multidecadal timescales. But the variability is not necessarily an oscillation where that would suggest predictability. And that variability appears to be caused to large part on this external, what we call external forcing, caused by reduction of stuff in the air, whether it's more natural stuff like dust or whether it's more human stuff like sulfate pollution. That is projecting onto that observed variability that we have historically called the AMO, but it's not natural. It's not internal. So here's the other thing. It gets really complicated, doesn't it? And I suppose that's job security for us. But the only thing internal and natural to this whole system that would, cause sort of a multi-decadal variability that's natural could be changes in the ocean circulation, what would be called the thermohaline circulation, or the Great Ocean Conveyor Belt, or the Atlantic Meridional Overturning Circulation, very fancy. That would be the natural or internal part to it. And there's a lot of debate right now about how much that actually contributes. Some people say it contributes virtually nothing. So, circle back, sorry for the long answer, but it's so important. It's such a hot topic right now. What is causing what we're observing, what we have observed in the Atlantic? It's very, very likely that most of that variability is due to external causes. It's not internal and natural to the system. There's also the idea of the volcanic eruptions and how that affects things, and that's completely random. There's no predictability in any of this. So the idea of the AMO is kind of dying. I think there would be people who would argue with me fervently about that, and that's okay. This is a really great discussion we're having in the community, but it does look as though that aerosol reduction, whether it's dust or sulfate or both, is a large contributor to what we historically call the AMO.
Paul, you got any questions over there you're reading?
Yeah, there's one here. I'll just read it. There's been a lot of talk about how to label and categorize hurricanes since the Saffir-Simpson scale is focused on winds. What are your thoughts about revamping, adding to, or changing the scale system to include a broader range of impacts?
Yeah, it's a discussion that's been going on for a long time, and ultimately this falls to the National Hurricane Center to make these decisions, because they're the ones communicating the risk. I think that there's always this sort of trade-off, and I'm a little bit outside my wheelhouse at this point, because this is almost more of a social science question than it is a physical science question. But there's a sort of a fine line between your messaging to the public and what you want them to take away and how you want them to respond, and some of the other aspects to how you might message things. Kind of a bad way to say it, but for example, when the National Hurricane Center can say something like, there's going to be, it's not a very strong storm, but there'll be this enormous storm surge, and I forget their exact words, but almost certain death. I mean, it was something really intense and profound in their message. And so they're kind of in that way on the fly addressing what you're asking about. Are there some other ways that we can message the risk? And there are a number of ways that you could potentially do that in terms of changing a measure to give a better idea of how much rain you're going to get relative to what you're used to in your location. I know there's been work that's been done that way. The idea of giving maybe a Saffir-Simpson type scale for storm surge would be in there. But again, it's a little outside my wheelhouse. A lot of it has to do with what the National Hurricane Center deems is best for their messaging. But there's no question that, again, all my answers are long. It's just my nature, I guess. But the vast majority of mortality is due to water, not wind. Right? Freshwater flooding and storm surge, saltwater flooding. Those are the two things that kill almost all the folks. The wind damage and ripping off a roof and maybe causing a tree to fall on a house. The mortality rates from wind are tertiary at best. And so the idea of having a warning scale based only on the wind does seem a little bit odd, but there's a historical context behind all of this. And Saffir-Simpson really originally intended it to be a kind of a catch-all, that the storm surge is wrapped up in this, and anything beyond Category 5, there's nothing left but debris to blow around, so it doesn't matter. So anyway, sorry, long answer, but
Love it.
it's dicey.
It's
By
a
the way, there was another question that follows up on this. Do you think there should be, with the the higher intensity storms expected, should there be a category 6?
Yeah,
Somebody's already
yeah,
asked that, and I thought I'd dovetail that onto the end of this one.
there you go.
it's perfect. Yeah, it's perfect. And in fact, we've sort of played around with that just to kind of look at how these extreme tails have changed and will continue to change in the climate models, and the idea of a category 6. So I've looked at that fairly carefully, and we're certainly would be justified at this point to have a category 6. But then immediately we end up back in the social science part of things, So if we introduce a category 6, are people going to start saying, it's just a category 5, I think I'm going to
Right.
shelter in place? So there's always that sort of human side to things in these decisions, but based solely on the science with no concern about messaging or anything, we certainly could have a category 6 at this point.
Just call it a category 5 plus. Just to
Yeah, right. Category
I think
5 on steroids.
yeah. I just like this question just because it's interesting to know where people are as they're watching this webinar or listening in. So Ryan Diacampo says, thank you for your comprehensive presentation, Dr. Kozin. Listening in from Philippines, based on your graphics, it seems that my country had fewer, stronger, and slower typhoons. Will this trend persist as the world continues to warm? Thank you.
Yeah, great question. The answer is maybe, and I know that's a very unsatisfying answer. In terms of model projections, which I think is really what we would need to use as a tool to answer your question directly. Our confidence in model projections is highest when we look at global behaviors. And the more we focus down to smaller and smaller regions, the less confidence we have. It has something to do with signal to noise ratio, but it also has to do with the fact that we're putting too much reliance on the models to actually capture these regional variations well. We have a lot of confidence that they capture global and, maybe synoptic, like, countrywide, nationwide, continent-wide changes. But when we zoom in all the way down to something like the Philippines, our confidence is less. So the way that I think about things like that is that I would say that if we have observed it and the models are predicting it in general, and we have a reasonable physical expectation, or at least some understanding of why that should happen, then at the very least you can say it's more likely than not that will continue in the future.
Okay, we got one here. This is from Justin Gertz, and I think it's an interesting question because it's kind of looking at it from a different angle. There's obviously been evidence of how climate change is affecting, intensity and things like that. Is there evidence on how climate change is affecting factors that negate intensity, such as vertical wind shear? So what are the things that are doing the opposite impact?
Yeah, excellent. Great question. Yes, there are. There appears global warming appears to increase the vertical wind shear in the deep tropics of the Atlantic, for example. So that would have an offsetting effect on the changes due to warming. So again, we start to get into, well, that vertical wind shear is certainly going to have a profound effect on genesis, because the storms, when they're nascent and forming, are very, very susceptible to wind shear. A mature hurricane, especially a strong hurricane, less so. They tend to create their own protective environment around themselves. But yes, there is an offsetting factor there. As I mentioned before, global warming also tends to stabilize and dry the air. Again, that would suppress genesis. Not as important for mature storms, again, because they create their own sort of environments within themselves. But yes, there are definitely things that will offset some of these factors. What's interesting about the Atlantic is that the warming is increasing the shear in the deep tropics, what we might call the main hurricane development region, but it's actually decreasing it off of the southeast coast of the United States. And there's some recent literature that shows that. So in that particular case, that you have a little bit of a wrinkle to the answer to your question. There's a pattern that can take place where in some places it offsets and in other places it enhances.
Okay, that makes sense. Paul, you got any good ones?
But I'm also watching our time because we're gonna
What time is it?
we are going to be wrapping this up at the top of the hour here. We have to. So I'll see if I can. I think we have a couple more.
One more
here.
quick question.
Let's see. Well, I know somebody asked, how do you explain to climate change deniers that lack of pollution could be regionally increasing tropical cyclones?
I'm not 100% sure I know where the angle that question is coming in from. I mean, there's always this fear that they're going to say, oh, well, we need to start polluting the air again to get rid of all of these hurricanes. And I don't think that's going to happen anytime soon. I think for the climate change deniers, they're more interested in how global warming is affecting things. I can't imagine they would have a big issue with the idea that reducing pollution warms the water. And the fact that that pollution is caused by humans makes it an anthropogenic climate change. It certainly does. But it's not the kind of anthropogenic climate change that climate deniers are generally focused on. So I don't really, I mean, if they do argue about that reduction of pollution warming, then they're just being contrarians, because it's just simple. If you put stuff in the air and you keep the sunlight from hitting the surface of the ocean, it's going to have a cooling effect. I mean, come on, guys. But I guess another way to say it is that I don't respond to climate deniers so much anymore. It's kind of a losing battle, and I don't think they want to change their minds. So we'll just forge ahead, and the smart people will keep listening to us.
Well, I guess that's a good one to end on there, Paul.
Now, this has been terrific, Jim. We can't thank you enough for taking the time to educate all of us about this. And this is being recorded. So the American Meteorological Society, once we get this recording posted, we'll have it on the AMS website. And either McCall or I will post it on the Broadcast Meteorologist Facebook page that many of you are on. And so if you or somebody you know, you either want to see this again, or you know somebody who missed it and wants to see this, you will have that opportunity.
Well, yeah, and thank you guys for joining us. If anybody has any ideas on what topics we should cover, because as Paul mentioned, this is going to be a series. So what other weather phenomena would you like to hear about that perhaps climate change may have an impact on? You can certainly send messages to Paul and I, and Jim as well. I'm sure he can pass them along to us as we are trying to figure out what our next topics are going to be with the AMS and the Station Scientist Committee. So thank you for joining us.
Thank you. Have a great day, everybody.